I think it's difficult to do it. So think of it, think of an element that's in the intersection of all RMs, and look at the set of elements in R that knock that back down into R.
I mean, I'm happy to do that. I think one of the things that was always hardest for me to grasp is what we're allowed to do with respect to saying like, oh, R1 equals R, really doesn't.
What is happening?
Yeah, you identify. Yeah, that's right. I mean, when you talk about fractions, you're talking about equivalence classes, really, aren't you? Right. So here's so last time we talked about well, I mean, are there any questions? Last time we talked about integral domain, or I'm sorry, we talked about UFDs, and the last thing we had was that any element that is a product of primes, or if you can express an element as a product of primes. Well, R product of primes. Then this expression, this factorization of primes, is unique. And I put unique in quotes because that's up to permutations and unit multiples. So actually, this is going to allow us to shortcut our notion of what a UFD is. But first, I want to introduce this. Let R be an integral domain. And S the set of elements that are expressible as a product of primes. Okay, so suppose I have an integral domain, and suppose I collect all the elements that are either units or they're expressed as product primes. And I could think of the units sort of trivially as products of zero primes in a certain sense. Then S is multiply closed and second. Okay. Units are multiply closed. Products prime are multiply closed. Right. So if I multiply unit by unit, I get another unit. Okay, back. If I multiply product primes times another product primes, I get a bigger product prime. So we got that covered. If I multiply unit times product primes, it's still product primes. Right. So the set is multiply closed. That's okay. What I want to do is show saturated. Also saturated. And to this end, suppose that X times Y is in S. . suppose I have two elements in R and X, Y is in S. Well, if X, Y is a unit, then X and Y are units. Right? And in fact, if one of X and Y is a unit, I'm still good to go, right? Because all I have to do is multiply this by X inverse, and X inverse times simplest product of primes is still product of primes, so good to go. So only need to worry when X, Y non-units. So I can assume without too much difficulty that X and Y are non-units. So suppose that X and Y, P1, P2, Pn. So in other words, since X and Y are non-units, it's certainly I can write it as product of primes. I don't have to worry about it being a unit anymore. I've already kind of taken care of that. And what I want to do is kind of proceed inductively as follows. So since P1 is prime, then P1 by X or P1 by Y. Right? You gotta love those primes, right? Since it divides that product, it has to divide one of the elements of the product, and we will say without loss of generality. P1 divides X. So I'm gonna write X equals X prime P1. So now let's just massage the equation a little bit. And what we get is P1 X prime Y is P1 P2 Pn. And so I get X prime Y P2. And now proceed by induction. Right. Now you kind of start over, you know, the P2 got to divide one of these and so forth. You eventually get down to the point where you're in unit. So the set's also such. Any questions? So let me finish my thought here. So that's one of the next two, both products of primes, because we exhaust that outline. Any questions on that? Okay, let me make an observation. And actually, I want to strengthen this observation with a really kind of a elegant theorem here. Theorem. An integral domain is a UFD if and only if every non-zero non-unit is prime. If and only if every non-zero non-unit of R is okay, so let me run through this just to kind of This way is actually given our background on these. Right? You know, every non-zero non-unit is a product of primes. Then it is uniquely a product of primes. So we get the uniqueness and primes. So I think that this crosses my T's and dots my I's. What do we know? We know every non-zero non-unit is a product of primes. I know that any non-zero prime in a domain is an irreducible. So that gives me my UFD signified irreducible. So now I know it's atomic. Everything is a product of irreducibles. But since they're prime, our previous results say that that factorization is unique. And so there we go. Right. The other direction. Suppose R is a UFD. It suffices to show that if R is a UFD and time in R is irreducible, then, okay, how many of you in grade school, high school, way back when, heard the definition that a prime is a number whose only divisors are itself in one, right? Really what they told you is that it's an irreducible. But guess what? The grade school or high school teachers got real lucky to play the lottery that day, because this statement right here shows you why this is true. It happens to be that the integers that you work with is a UFD. So any non-zero irreducible is in fact prime, right? And so that's why the equivalent definitions work, because C is UFD. Of course, more generals, irreducibles and primes can be different. So let's see why this is true. Why is it true that in a UFD every irreducible is prime? So suppose right? Well, this means that AB R for some R and R. Right? Now here's the thing. As R is UFD, then A is equal to and B is with A to I and omega J irreducible. Right? So this is a unique factorization. So what I've got is I've got a bunch of these crazy Greek letters. Right? Now, of course, the right-hand side of the equation can be factored into irreducibles as well, and it has to factor the same way, right? Up to permutation, right? So in other words, pi up to a unit has to be one of these or one of these. Agreed? If it's one of these, then pi divides A, and if it's one of these, pi divides B. So pi is associated to some And here, associated, if you haven't heard that before, that just means it's a unit multiple of one of these. In the first case, there is a slight incompleteness in my proof because I'm assuming that neither A nor B is a unit, but if A or B is a unit, it makes my life easier. Right? Because, for example, if A is a unit, then I must divide B, and if B is a unit, I must divide A. And they can't both be units because then it's not irreducible or not divisible to any irreducible. Okay, any questions so far? This is powerful because this, if you introduce the concept of prime as opposed to irreducible, this gives a much easier characterization of UFD, and that is R is a UFD if and only if every non-zero non-unit can be written in product primes. Right? You don't have to write any of this stuff about the irreducibles and carrying them off, whatever. And so I can't resist following theorem. And so here is the daddy Mac, so to speak. And I'm going to write this way. Let R be a domain, the following conditions are equivalent. The following are equivalent. Number one, R is UFD. Two, ever non-zero prime ideal E and R contains a prime element, a non-zero. And three, okay, these following conditions. Number one, R is a UFD. Number two, and this is what really neat. Every non-zero prime ideal contains a non-zero prime element. Now, this does not mean that the prime ideal P is generated by that element, right? So for example, let me give you to kind of illustrate this. Suppose F is a field. How many of you are familiar with this? That a polynomial ring over a field in any number of variables is a unique factorization. Right? You have unique factorization. We'll get to that later. Here's a non-zero prime ideal. And in fact, this is a maximal ideal. And there's a non-zero prime element in it. As since this is UFD, this must happen. By the way, there's a whole horde of prime elements in there, right? X plus Y, X plus Z, Z plus X plus Y, X, Y, Z, all these are prime. Right, but there has to be at least one non-zero prime element in any ideal. Now, the important thing about this is the definition of UFD is an element-wise definition. You're talking about elements and, okay, they factor into these strings, other types of elements called irreducibles, and whenever you do it, it comes out unique, right? It's an element-wise thing. This is an ideal theoretic characterization of that element-wise result. And when you see that, that's also a good sort of hallmark that this is a good property. And actually, later I will probably do a number of proofs of theorems that you probably at least know by folklore. And I'm going to use this characterization to, it simplifies things quite a bit. Actually, when you have something that has, when you study factorization, so this is sort of a plug if we want to do this topics towards next semester. In factorization, there's lots of different classes of factorizations. There's UFDs, there's unique factorization domains, there's half factorial domains, there's finite factorization domains, there's ACCP, there's just generally atomic, and of course there's the VFDs, and they're a real VFD. But anyway, all of these discuss factorizations in terms of elements, right? Only UFD has, as far as I know, only UFD has a really good ideal theoretic characterization. The other weaker factorization properties, you don't get theorems that are as good. And the reason you don't get theorems as good is because it doesn't have that ideal theoretic characterization. In fact, for half factorial domain for HFDs, which means, if you don't know, just for interest, it means that you might not have unique factorization, but every time you factor something, you find that it has the same number of irreducibles in factorization. They can behave badly, but there are certain cases, for example, in rings of algebraic integers, when HFDs do have an ideal theoretic characterization. And in these settings is where you get their best theorems. Okay, so there's my philosophy. And finally, this last one I couldn't. Does anybody see the difference between this one and the original characterization of UFD? There's a subtle difference.
Not acquiring them. You're ignoring the M equals N. So
That is correct. So what this means is the third characterization means to be a unique factorization domain, all you have to do is check all the same length factorizations and see if they're the same. Right? You know, if all the same length factorizations are the same, it's impossible to have different length factorizations. We're not going to prove this one because that one's just requires more machinery. Okay, so let's go through this because this is like just too fun. We will prove the third one's kind of, like I said, tack on fun. Maybe we might look at that in a different course. Proof. Let's assume first that R is UFD. And what do we want to do? We want to show every non-zero prime ideal contains a non-zero prime element. Okay. Guess what? If I've got a non-zero prime ideal, it better have a non-zero element in it, right? So here we go. Notice that P is not a unit, or I'm sorry, X is not a unit. Because for crying out loud, it looks at an ideal, right? And it's not zero. And so since I know that X is a non-zero non-unit, guess what? It has to factor unique, it has to factor into primes. Because we already do have that equivalent for UFT. Prime. And guess what? Right. So, for some this is a prime ideal. So since that product's in there, one of those has to be in there, and there we go. E contains non-zero. So that was the easy direction, right? If it's UFD, this certainly has to happen. Of course, the interesting part is why is this condition good enough? Right? I mean, if you think about it, it's kind of weird, right? Because all it says is if you've got a ring and if you isolate any non-zero prime ideal, you can find a little prime element in it. If you do that for every prime ideal, non-zero prime ideal, that means that you have to have unique factorization. That's kind of cool. So to this end, well, let's do 2 parts. One, let us do the set of elements of R. They can be written as a product of units. Let me tell you what I mean by this. Basically, what S is, it is the smallest multiplicative set that contains all the units and all the primes. So it's everything in there. It's either a unit, it's a product of units, or it's a product of primes. And the units times primes is the product of primes as well, right? This is like that multiplicative set that we discussed in, I think it was 147. So let's let S be this set. So to show this a UFD, it suffices to show that S is basically all the non-zero elements, right? Because if S, that is the set of things that can be written as a product of units and primes, if that is all the non-zero elements of R, then what have we shown? We've shown that every non-zero element of R is either a unit or it can be written as a product of primes. That's all we need. So let's do this. And here we're going to see kind of the power of this business that we talked about with multiplicative sets and ideals. If not, there exists X and R on 0 that cannot be written as a product of units primes. So suppose you have a road here. Now consider the ideal generated by X. That if you can find this rogue X that doesn't live in S, then in fact the ideal generated by X is also. So not only does X miss S, but every multiple of X misses S. Anybody recall why?
Having multiple X, right as prime, this. Someone doesn't have to divide X. So,
That's right, that's right. So you went through the proof, that's exactly right. Recall. As the same. So, here, R X is in the S. Then X. So indeed, this little principal ideal misses the set S. And so what's our big theorem? We can sprinkle the fertilizer on it and grow it to a prime ideal. You grow it to a prime ideal. And somebody please tell me what's the problem here? Yeah.
based on all this, you have to have a non-zero prime element that you can add into the time, that's.
That's not the thing. Prime element. As those law made mass. Right, therefore. Or, and this is prediction. So, S is R minus 0, and R is. Okay, any questions? Any questions on this? Okay, let me throw in an example because I do so love examples. And this illustrates a point. This illustrates 2 points. It illustrates actually the importance of an underlying assumption that we've used through all of this theorem, although it certainly would be used in this application here with the multiplicative set, but an underlying thing is it's an integral domain. So you might say, well, can you extend this? First of all, one of the problems is what do you mean by unique factorization and something that's not a domain? Let me give you the following. This ring is certainly not a domain. It's chock full of zero divisors, and it has precisely 3 proper ideals. Not counting. You've got this, you've got the ideal 0, 2, 4, and you've got 0, 4. Right, so these are the 3 proper ideals. This one is not prime because this is not in there and this is not in there. Prime 2 bar, 3 bars in there. In fact, 0 is prime ideal if only parts of the domain. So that's off the table. However, these 2 ideals are prime and they contain prime elements, right? It's certainly non-zero, right? Because those elements generate the ideal. However, factorization is not unique, and you'd have to discuss what it means, because, for example, 3-bar. Three bar is in fact item, so it's a real obnoxious sucker, right? Because that prime element, right, generates that prime ideal. Well, so yeah, the question is the question also is, right, yeah, so 3-bar generates this prime ideal, but I mean, it's not irreducible. Do y'all remember how earlier we said that in a domain, that if you have a prime element, a non-zero prime element is irreducible? Here you see a problem. Here's a situation where you say that, see the domain is problematic, right? And it's the zero divisors that are a problem, because I mean, if you just take this part of the equation, you get 3-bar, one bar minus 3-bar, 0-bar, pulling the total factor into 3. But of course, this is 4, right, which is it's a zero divisor, and so it's problematic. Yes.
So you said you talked about those two ideals being prime, and then you said that 2 and 3 were generators, so they were prime. But isn't and that's true in this case, but isn't that only true in a domain in general? That if you have a physical prime ideal, that the generating element is prime, that we need in an integral domain. That's true.
I think if you get an element generates, there might be a problem. I mean, it's true in this case, right? What do you think about that? Because if you have
Like the backward search, the forward direction, works always.
yeah. So yeah, so you might have a theorem that says that. So let's find that out. Choose that. Let's see if that works, right? I'm not sure. So let's try to do it. And here, I guess we're gonna have to agree on what the definition of prime is, not the thing. X divides AB implies X divides A or X divides B. So that'll be my playground rule. Now, this is a non-trivial step in general, because when you go to rings that have zero divisors, you have to agree on what it means to be irreducible, and there are at least 3 tiers of that. It's difficult. Let's just take this to be the definition. So let's go this way and see if we can prove it. Suppose that we have this property here. We want to show that X is prime ideal. So suppose AB is in ideal number by X. So AB of X, some R and R, right? And therefore, X divides AB. So X divides A without loss of generality. Therefore, A is in diagonal X. So yes, this direction, no problem. What about the other direction? For the other direction, suppose well, let
Are we assuming community?
oh yeah, yeah. I mean, you take everything away from me, man. So, yeah, we're all
So
sounds.
please do.
Yeah, because-
I don't want to do it, but I need to.
Right, in the non-commutative case, you can't even do that element wise.
Yeah.
Definition of time, it's more complicated. So, let X divide AB, and we want to show that X divides one of them, kind of hope this is true. This means AB equals R of X. Which is, in the ideal boundary line. Therefore, without loss of generality, A is in the ideal generated by X. Therefore, A is equal to R, well, let me say R prime X. So, X. Yeah, so I don't think you can worry about zero, but prime's good. Okay. Right, so this next result, actually is kind of neat because from one perspective, you can think of this as a way to use modules to build prime ideals. So, let me clarify that a little bit. Like suppose R is a ring and A is an R module. And an R module. If I is any ideal that is maximal among annihilators and non-zero elements of A, then I is prime. Suppose it is maximal among all annihilators. The non-zero elements of A. Non-zero elements of A. Then I. So let's prove this. And I think the proof will kind of give us some insight as to what the theorem is saying here. Proof. Well, I didn't this follow actually. Let I be the annihilator of some A and A. By the way, you know what I mean by the annihilator of A? In case there's, so that is. So it's basically all the stuff in R that kills A, that smashes it zero. And notice that if A is a non-zero element, then one is not in there. Right, and so this is a proper idea. It's pretty easy to see it's an ideal, right?
And that's for all A and A, right?
No, this is a particular A and A. Oh, so yeah, so I've just got some element.
Oh, right.
And I might write the annihilator of A or the annihilator of the ideal generated by A. Suppose X, Y is an I. And of course, if I want to show this primes strategy, so if Y is not in I, that means that Y does not kill X, right? So YA is not 0. But note, so X is actually an annihilator of YA, which contains the annihilator of Y, or I'm sorry, the annihilator of A. Right? So if I is maximal, annihilators of elements of A, well, not 0 elements of A, right? So if I now throw in that, okay, I is maximal among annihilators of non-zero elements, then this must be an equality, right? Because this thing is I, this is a proper ideal that contains it, and it has to be equal if I is maximal among these annihilators. Otherwise, you've got to figure an annihilator. Therefore, X is an I. Well, what I was saying. Right, no, therefore, this must be an equality, so X is an I. And I. That's a cute little proof. And I'll kind of talk you through this. I'm gonna, a lot of you know this already, this is a famous, I'm going to couch this in terms of a proposition. I'm going to use it to define the so-called Noetherian rings. Proposition 1, 4, 11. Let's R be communicative identity. Following conditions are equivalent. Number 1, any ascending chain of ideals stabilizes. Let me make this more precise. Given I1 contained in I2, contained in I3, contained in then there exists in the natural numbers such that I n plus k is equal to I n of k in numbers. So in other words, there is a point where it has to stabilize. You can't ascend forever. At some point, you have to become the same ideal. And number 2, every ideal of R is fine. such a range is called Noetherian. Any ideal that satisfies the ascending chain condition on ideals. Equivalently, all ideals are finitely generated. Equivalently, and we'll prove this later, all prime ideals are finitely generated. You only have to check the prime ones. That's another kind of hint that Noetherian is a really, really nice problem. Okay, any questions? Okay, let me plug the math club. Michael Burr's going to be there today doing some origami. It should turn out to be the social mecca of the Western world. I would encourage you all to be there. Good time will be had by all. Yes, there will be. That's the rumor anyway. All right, y'all have a good weekend and we'll see you then.